All right, so limits have several different applications in the world of calculus, and we're going to talk about the first one here, which is figuring out a derivative. So in order to have a slope of a line, we've always learned that you need 2 points, correct? Like you would need a point here and a point here, and to find the slope of that line, you would need these 2 points. Well, we call that a secant line, and you find that slope if this is where we're going to say this is x equals a, and then this is just some arbitrary x value out here. Then you're going to find your change in y over change in x. So x minus a is in my denominator. These 2 function values go in my numerator, and that would find me the change in y over change in x, or the slope of this secant line. Another way that we can write this is by saying if this is a, then if you add some arbitrary h value just to that a value, then this x would be a plus that. And so notice in this equation here, in place of x, we put a plus h minus f of a, and in the denominator, a plus h minus a just simplifies to h. So we call this the difference quotient. It still is the slope, like that's still a true thing. And you can find the difference quotient on an interval containing a as long as x is not a. Remember, we need 2 points in order to find the slope. And here's some kind of graphs to show you what I was showing you in that picture. But in calculus, we don't necessarily want the slope of a secant line. We want the slope of the tangent line. The problem kind of being here is that's only 1 point, and I need 2 points to make the slope of a line, to make any line. So we're going to use this concept of limits and say, as I take x and get it really, really, really stinking close to a, so I'm going to move x into a, and I'm going to take infinitely many, I'm not drawing very good lines here, but infinitely many secant lines until I get really, really close. Like x is still not equal to a, I still need them to be different points, but as x slides into a, that secant line slope curves down and becomes the tangent line slope. So that's where the concept of limits are going to play here, is you are going to take the secant line, you're going to slide x to approach really close to a, and that's going to give you the slope of your tangent line. If we let this value of h here go to 0, what that would mean is a plus h would get really, really close to a. And so notice this is the same concept, just with h going to 0, if we have that like second value here of a plus h, like in that previous graph that I showed you. So in place of x, I put that a plus h, and then we're going to, again, let h get really, really close to 0 so that a plus something really, really close to 0 gets close to a. All right, so instead of writing that m10 or msec notation, what we are going to use instead is we're going to define that f prime of a is what we're going to call the slope of the tangent line. Now f prime is what we call that. F prime is the same thing as the derivative at x equals a, and all of these things are the same thing as the slope of the tangent line. This is also known as the instantaneous rate of change, where a secant line would find you the average rate of change, a tangent line finds you the instantaneous rate of change. So that's what the derivative is going to find us. All right, so let's use that first equation to find the equation of the tangent line to the graph of f of x equals x squared at x equals 3. Well, let's just kind of draw what that would look like. So I have my parent function. I'm here at x equals 3, and I want to find the equation of this line. So I'm going to use point slope form in order to do that. And I know that this is the point on the graph, 3, and then 3 squared would be 9. The question is what's the slope of that line? Well, it's a tangent line. It's not a secant line. There's only one point. So I can't use our traditional form of slope here to find it. So I'm going to use that secant line and then move it into become the tangent line. So let's just say arbitrary x value. So f of x minus f of 3 all over x minus 3, right? That would be our 2 points for our secant line. And then I want to get as close to 3 as possible. So I'm going to say take the limit as x goes to 3. All right, so that's x squared minus f of 3 we said is 9 all over x minus 3. And again, I'm taking the limit. And if I plug in 3 here, I get a problem with my domain, but x squared minus 9 does factor into x minus 3x plus 3. And if you notice, that then cancels out like what's causing the issue in the denominator. So this is going to be the limit as x goes to 3 of x plus 3. When I plug in 3, I get 6. So that's my m. So my y must be equal to 6. X minus 3 plus 9, and that is the equation of that line tangent to the graph of x squared at x equals 3. All right, let's do another one here. Now I'm looking at 1 over x. And I want to find the equation of the tangent line at x equals 2. So that's 1, 1. Here's 2. And then what would that be? 1/2. And I want to find the equation of that line. All right, so again, let's just use that same x minus a equation. I personally find that one to be the easiest. So we set this up as f of x minus f of a, that's my a that I'm trying to find, all over x minus a. So again, I'm finding slope, changing y over change in x, and then I want to get ridiculously close to 2. All right, so this is going to be the limit as x goes to 2 of 1 over x minus 1 over 2 all over 2. Now, if I plug in 2 all over, sorry, x minus 2. But if I plug in 2, I get some issues here, right? Let's go ahead and find a common denominator here of my top piece. So I'm going to do that by multiplying this by 2 over 2, multiplying this by x over x. And I get the limit as x goes to 2 of 2 over 2x minus x over 2x all over x minus 2. I'm going to combine my numerator. And then notice here in the numerator, it looks very similar to our piece down here, but it's like in reverse order. So if I rewrite this as negative x plus 2 and then factor out a negative 1, oh, I forgot a 2 over here. Here we go, okay. If I factor out a negative 1, I'd be left with x minus 2 all over 2x. And then I need to multiply by the reciprocal of the bottom if I'm dividing. go ahead and cancel my term that's kind of causing my issue, if you will, when I'm trying to plug in 2. And so I end up getting the limit as x goes to 2 of -1 over 2x. Let's plug that in. I get -1/4. Now remember, that's the slope of my tangent line. That's the same thing as saying f prime of 2. That slope is -1/4. So let's go plug that in. Oops. Let's go plug that in to our line up here. Now, it also makes sense that my slope is negative because my graph is decreasing. So it makes sense that tangent lines like that has a negative slope, right? So it makes sense when I'm plugging this in that that's going to be the equation of my line.